All right. So yeah, I'm Neel, and I build and maintain SDKs at Sentry. These are some of the SDKs I work with. So I'm mainly the maintainer of Python and Ruby, and then I usually read and sometimes once in 6 months contribute to the JS repo, the PHP, the Go. I also I do some Rust once in a while because that's like our geographically distributed sort of ingestion pipeline. And then I also work on our monorepo Sentry, which is like a classic Django, TypeScript, React SaaS product. So I wanted to talk about building stuff in many languages because there's usually a lot of context switching involved and so on. So let's go through it. So I always like to start by making fun of the audience because this is what most people today in the industry do, which is they're like full stack developers, and that's me on the right, because I work in many languages. So. So yeah, what most people do these days in the industry, at least like 80 to 90%, I would say, is like they work with some backend language, Python, Django, or Ruby Rails, or some Go backend, or some Node.js backend, and they then usually have some front end like JS, React, Vue, or some stuff like that. And usually that involves, I don't know, making endpoints on the left, making some APIs, making some functionality, talking to databases, and then on the front end you like render stuff, and yeah, that's basically what. But what we do at Sentry is we're building stuff for you guys. So we are like slightly lower in the stack, but we also work across languages, and we want to sort of do the same thing across languages. So I don't know if everybody knows what Sentry is. If you don't, please talk to us. We have a booth outside. But overall, we basically build libraries for error monitoring, for performance monitoring, profiling, and so we want to hook it into your application and give you lots of insights about what's going wrong with your code. And then, so we want to make abstractions that sort of work across the semantic differences of each language. And there's some complexity and a lot of things we've learned over the years about how to deal with those differences and then sort of make something that works across everything. And sometimes it also doesn't work. So I'm also going to talk about those things. So this is the rough problem space that I will be talking about. API design is very important because it's like what the user eventually ends up using, and we want to keep that as simple as possible. There's also and the main differences come from like dynamic versus static type languages, like Python, Ruby, JavaScript, and then you have stuff like Rust, Go, and then lower level C, C++. I won't talk about those. In many languages, you can do monkey patching, like Python and Ruby, you can, and that makes it a lot easier for us to build libraries for you guys. And then in static languages, there's like stuff that goes wrong because we can't really do stuff we can in dynamic languages. So I'll talk about monkey patching a bit later, and then concurrency is like a huge area because every language has different concurrency models, and then you have to somehow abstract over those because we want to do stuff that also works across sort of concurrent programs. And I'll talk about packaging, like the ecosystem, and then finally, actually, the most interesting probably is just the human factors involved in doing all of this. Let's get into the meat. So API design. Sentry, we want to build a library for that is very, very simple to use. We want you to add just one line of code. You install the package, you do sentry.init, and then it just works magically out of the box. It does a bunch of stuff. It will capture exceptions, it will do performance, and this is our goal. Like we want to hide all this complexity from other programmers so they can get on with their daily job. Like we don't want you to think about other stuff. And so we want that magic to happen, and we want a consistent user experience. So we want to be as close to this API design as possible, because it's also important for adoption. It just makes lives easier, and there's also engineering. We're supposed to make everybody's life simpler, not more complicated. This is like a core design principle, and we try to do that. So in Python, you can actually do that because we monkey patch a lot in Python, and people of course get scared of that because then you don't know what's happening. But it's on us to that's our responsibility to take care that we don't break any contracts and so on. That init call will basically do a bunch of stuff. It will go through your frameworks. It will go through. It will detect a bunch of stuff, or it will patch a bunch of functions and then hook into stuff, and it does a lot of things. But the end user doesn't have to think about all that, and that is possible in Python and Ruby and so on because you can patch stuff. On the other hand, the same thing in Go looks like that. And that's just a lot of cognitive overload for the end user that we don't want to expose, but we have to because in Go there's no choice. Because you have to compile stuff, things that check the compile time. There's a lot more manual stuff. So if you want to capture exceptions, you have to wrap the handler of your HTTP server, like here it's sent fast HTTP, and then you have to force the user to do all this stuff on their end, which breaks the sort of simplicity of our API that we have in some languages. And so that's like a big difference. You force the user to do stuff in their application, and that's just a lot more cognitive overload to deal with and so on. And we want to avoid that. So I will talk about possible ways to avoid that as well. Yeah, the main differences come between, like, this is one of the biggest differences between dynamic and static languages, as I said. So monkey patching is a huge thing. So dynamic, you can't monkey patch. Static language, in dynamic you can. In static languages you cannot. And then dynamic languages have duck typing usually. So you can just send random stuff to a function, and it's like maybe breaks, but like you can just make changes. In static, you have to make everything compile time. So if your language doesn't support generics, for instance, then everything gets way more complicated because you have to build everything for every interface and so on and so forth. What is a breaking change? As a library author, breaking changes are always like a big issue. So in dynamic changes, again, contracts like APIs are much simpler. You can keep the same API and just change everything under the hood because like nobody cares about types. But in type languages, then you break stuff way more often because if the API change, the types change, then that causes much more churn in terms of breaking changes. So, and then introspection, like, just as I said, like, we try to detect what frameworks you have and stuff. So you can do that in dynamic languages. But in some languages, you can't like introspect at runtime what all is running in the environment and so on. So it's just like dynamic just gives you way more room to play around with stuff. And then static is, of course, way more secure and safer, like, because you have all this stuff, but then you lose that sort of flexibility to do stuff. So that's like a big trade-off between the two. Yeah, let's go over the monkey patching. I just saw this on Twitter a few days ago, and it said just big and greedy, and I think this monkey has cool energy. So he just cares about its mango and nothing else in the world. So yeah, what is monkey patching? So I don't know if you know what monkey patching is, but monkey patching is basically at runtime you can just change whatever. If a class, you can change a variable, a function, you can just change the function on runtime. So if a class is a foo function, you just say this class foo function is something else now. You can do that in Python, you can do that in Ruby. And that's very dangerous, of course, because you have to think about a lot of things. We have to be very careful when you do that, especially as a library author for everyone. We have to preserve contracts. We have to preserve what's something called idempotency so that you don't sort of break user behavior. But let's look at an example here. So let's say you have some class, and there's a function just like does something, returns a variable, or just returns a number. And what we do inside Sentry now is we basically patch your function. This is roughly how Sentry works without all the bells and whistles. And we take a reference. So the old bar is like a reference to the original function, and then we make a new function which calls your function. And if there's an exception, we send some information to Sentry over the network, and we re-raise the exception. So the re-raise is very important because that's the idempotency. We didn't change the behavior of your application, but we did some extra side effect on the side. So yeah, this is how a lot of like performance monitoring also works, because you trace some timing. So you get, instead of the exception, you can have some timing around the function, and you can measure the time of that function. And so you have inside, you have observability into your application, but you did not change the end user behavior. That is very important. So this is called idempotency, which is you just inject the side effect, but the original code stays the same. It does some extra stuff, but it doesn't change its sort of business logic at all. But in static languages, you cannot do that because, you can't monkey patch. You can't just change a variable. So instead, so this is a Rust example now. So you have the same kind of function. Of course, it's typed, so it's like it knows that it returns an integer. And then you have to make a wrapper function. So you have to expose a wrapper function that takes the original function and then does the same thing. So like Rust doesn't have exceptions, so it's just gonna do that result stuff, match it, and if it's an OK, you just do return it, and if there's an error, you send stuff over the network. But now the important thing is in Python, the user didn't have to change their code at all. They just needed to call sentry.init. But here, the user in their own application code will have to wrap their function with the Sentry wrapper, because we can't do that. We can't do that at compile time. So this means that the user, if they want to do stuff in their application, they have to go and change all of the instances in their huge code base wherever they want to do Sentry stuff. And this like adds a lot of overhead to adoption as well, because people don't have time to just to do all this stuff. Maybe, I don't know. So yeah, it's a lot more manual. Sometimes as I also said earlier, if generics are not there, so Rust has generics, but maybe Go doesn't, and then it's even more complicated because maybe you can't compile even, like you have to expose wrappers for every kind of type, and that maybe it just doesn't work. So yeah, that's the complexity we face. Another example of just stuff getting lost in translation. So I'm actually a Rubyist. Like I did Ruby for a long time, and I do both Python and Ruby now. But sometimes because in Ruby you don't have to write the return statement at the end. And I've actually pushed many PRs where I forgot the return in a monkey patch. I forgot the return in Python, and that actually breaks the contract because you have to explicitly return. There's very simple syntactic changes. Like, Python and Ruby are like very similar languages. You can just translate between them freely. They do more or less the same thing. They have objects. They have functions. That you can put some state on the class, but it's just that because you're so used to like writing certain, because in Ruby I just like flow. I don't have to think about it. I just type. In Python, I have to then like do this bit of translation. It's the same when you speak a human language. You're learning a new language. You sort of you keep translating till you get to the point where you're so comfortable that you just start speaking it itself. Like it's I think the same sort of principle holds here. And so I just wanted to give a very simple example of like mistakes that you can do when you're like constantly context switching between languages. This happens all the time. And it's just kind of annoying. Let's talk about concurrency now. So this is a huge topic because what Sentry as a performance monitor who wants to do is we want to track state even when you're like doing stuff across concurrent execution stuff. We want to track state, and now the language space is so complex because everybody's trying to innovate and make like the concurrent stuff better because it's like a huge unsolved problem in computer science in general. Nobody knows how to do concurrent programming well. I mean, we're getting better now with the newer models, but you would start off with the classic threads model. In Python, Ruby, Java, you have like threads or green threads or whatever. So threads are basically things that fork off and they carry some state in itself, and then you have problems with like sharing that state across threads. So you have things like locks and mutexes and synchronizing and so on. And this is just a very like sort of fragile model to work with. And so people sort of make async await and tasks, and then Python and Node, you have like promises and stuff. And that makes it a bit better, but then, it's still very confusing because you have this sort of, red-black type of thing. I don't want to get into too much into that. And then Rust has futures, which you sort of run in some runtime, which is also similar to async await. Rust also has async await now. And then Go came up with this completely different model called coroutines, which is like, you write two Go functions and they can talk to each other over a channel. And then, so I think there's like a lot of the concurrency space is going towards like sharing less state and instead message passing. And this is obviously pioneered by the Erlang model, which is the actor model where, you have these very lightweight things that talk to each other and then pass messages and then react to those messages via message queues and so on. So, this is like I think the spectrum of concurrency is like, threads versus like this message passing type model. And the thing is, when we build some SDKs, we want to abstract over all of those. Like, we want to, let's say you have, we want to follow some state across async computation, and that's actually a tricky problem to solve. Because, let's say you have some authentication thing in your app, and then you set the user, and then you spawn like threads or tasks or futures or whatever. Like you start 3 different async things. But we want to track that state across all of those threads. So and then something goes bad in thread 2, and then we want to report that exception, and we still want to know that this was linked to that user. But because thread sharing state is such a big problem, it's not an easy problem to solve. So you need to do some extra bookkeeping across threads. And then, how are we going to share that state? Like, if you're just trying to solve this problem, do you do locks? But if you do locks, then that solution is not going to work for async IO or futures and stuff like that. And it does just like this. If you just make a solution just for threads, it's not going to work for like message passing type designs. So this is kind of a tricky problem to solve. I actually don't think we have even solved it satisfactorily, but we have some sort of solution which kind of works. So what we came up with is like, you just have a bag of arbitrary state, which is immutable. So you copy that thing, you have some bag of state, and then you copy that thing every time you start a new async computation. And then you can store the state that you want in that. But because it's immutable, you get rid of the lock problem and so on. So Sentry does it by something called a hub, which is just some name. It's like a very abstract thing. But it basically carries a stack of objects that you push and pop. And then you copy that over whenever you start some concurrent computation. OpenTelemetry actually calls this context, which is also like just an arbitrary dict, which is also just copied on whenever you want to use it. And this is like from the OpenTelemetry spec actually, which is a context is a propagation mechanism which carries execution scope values across API boundaries and between logically associated execution units. So that's a lot of words. But the main thing here is the execution unit. So what is an execution unit? It's like a thread, a task, an async IO task, a future, a coroutine. These are all execution units because they're sort of doing some work separately on the side. And so, we clone this bag of state on each execution unit. And yeah, we do that for all of those structures, for threads, for tasks, for coroutines. So again, for static languages, this responsibility is passed to the user. So every time they set up, say, a Go routine or something in Golang, they have to do this themselves. So they have to do this cloning themselves. So they have to call Sentry and then do sentry.hub.clone. And even for Elixir Erlang, we haven't even like come up with this because that's sort of lagging behind in implementation. And it's like an open problem how we're going to solve it because it's like a completely different design, and I actually don't know how to solve that there because the work is not instantiated there, but it's actually always exists and restarts on crash, and then you don't know when to clone. Like if you just clone at the start of the application, it's not going to work because you need to be able to add state later on, and yeah, so that's an open problem. We'll see what to do about them. And yeah, just to bring it back to the whole dynamic static discussion, what I said, so yeah, in Python and Ruby, we can just patch the threads. We can say, okay, whenever the thread is starting, when it's running, we just do some extra Sentry stuff, and then we call the original run. Same for a task. Like we hook into the task factory, and we just do our stuff, the cloning stuff, and then we let the user do their stuff. But in static, again, either you force the user to change all their call sites. So whenever they're spawning a thread, whenever they're doing a coroutine, you have to add all these clones yourself, which nobody's going to do because it's just super annoying. But what we can actually do is expose a wrapped interface. So we can either work upstream with language people. So we can talk to the Rust guys on GitHub and say, okay, can you guys expose a hook that we can use then to do some extra stuff? But that, of course, is a longer sort of development cycle. It might take 6 months till like it goes through the whole RFC process and so on. And yeah, but we still do want to do that eventually. Or we can expose a wrapped interface. So this is a bit easier to refactor because the user just has to change the input. So if in Rust they're doing an std thread spawn, we instead expose a Sentry thread, and they just basically need to find and replace all imports in their project, and then it just kind of works because we expose a thread interface that sort of hides the complexity. Yeah, so this is like all wrapping up on the whole API design, monkey patching, dynamic static discussion with the concurrency stuff. All right, let's talk about some simpler stuff. Yeah, the concurrency stuff is a bit complicated. Packaging is also very interesting because we have to release stuff to all of these different ecosystems. So we have the PyPy, we have Ruby gems, we have NPM, Maven, Rust Cargo, and so we actually built some tooling called Craft, which uses GitHub Actions and so on to publish packages to each of these, because it's like a deploy thing, but for each sort of language ecosystem. Semantic versioning is a big topic because it's actually very complicated because nobody knows what a breaking change is. Like, everybody talks about majors, minors, and patches, but what is a breaking change? So because we build a library that actually talks to a system outside, like because it actually goes over the network, and then Sentry actually has a monolith. Does a breaking change mean just like when I break something in API in my library, or does it mean that I broke some or macroscopic behavior that like if it's talking about a network, does the other system count as a breaking change in my library? Because it's still like a holistic system, but so this is always like very, and we have like huge debates about what is a breaking change and what is not and so on, and sometimes it gets a bit out of hand. And then yeah, different package managers also have different differences. So how do you deal optional dependencies is a very interesting question. So Python, for instance, has extras. In the setup.py, you can say these are extras. So you can say if Flask is present, you install some extra packages and so on. Because the SDK we want to keep as low dependency as possible. So the Python SDK has only 2 dependencies, only certify and URL lib3. So it's only using like these very 2 low-level libs because we don't want to impose dependencies on user space. So that's very important for us. So in Python, we can do it with extras. So if you say Django Flask, we can just put them as extras. But in NPM, for instance, it's not possible. Then you can either go the peer dependency route, or you make like separate packages for each sort of integration. So you make a Sentry Node package, a Sentry Express package, and so on. So, and we have that in JavaScript, for instance, where we have different packages for each sort of framework and so on. And this also affects like repository design. So is it like one big multi-repo, or is it like split it up into different ones and so on? Sorry. Yeah. And then let's maybe talk about human factors, because this is also very interesting. Because when you have to do the same stuff across so many different packages and languages and people, you need a lot of processes to sort of make sure things happen. So one consensus is always a very hard problem. Because you have too many smart people in a room, everybody has opinions, and sometimes people will debate for 3 hours on some like really small difference. And sometimes as engineers, it's actually important to say, hey, like, we just stop debating, just do something, we ship it, we'll see what happens, right? But, and so you need like somebody to drive stuff. So we also have we have weekly meetings where we try to reach consensus on things that we want to do, because sometimes you need to run it by other people. We have RFCs for even more technical things. So we have and it's all out in the open. It's on GitHub. You can follow our processes everywhere. And then sometimes they last weeks because everybody has a lot of comments, and then hopefully we reach like a conclusion on what we want to do, and then we ship and implement that. Yeah, and this is just like sometimes it feels like this Jedi. I don't even like Star Wars, but sometimes it's really some of the consensus stuff really feels like trying to convince a lot of wise old people about stuff. And then also legacy is a huge problem because things you did long ago, especially for library development. If you're just building a SaaS product, you can break stuff. It's okay. Like you can fix it in 2 hours, right? It's not a huge deal. But for libraries, like our contracts with all of you, and then you can't always break stuff that easily. So we have a lot of historical package, and pushing majors is not always like acceptable for small breaking changes. So it's just sometimes it's very hard to work around sort of not breaking stuff and legacy stuff. You need to justify it in a very sort of solid way. And so I'm gonna wrap up now. So just like what I was basically talking about is doing stuff in many languages. So like any language, reading is a huge part. I read a lot more code than I write in many languages because I'm just trying to see what my colleagues did somewhere, and then I'm just like trying to replicate it, translate it over into some other language. And then you write stuff. You learn to write stuff in many languages. It takes a while because there's a lot of context switching. You learn to express yourself slowly. There's huge learning curves for some languages. So something like Rust is like way harder than something like Ruby or Python. And then you learn to translate between all of those. Sometimes just writing is a very simple piece of code in Rust. It's like it takes a long time with a borrow checker and stuff. And design and architecture is very important because we are trying to build interfaces for actual programmers, and we want to keep them as simple, as easily understandable as possible. But sometimes you end up exposing a lot of complexity, and it's not always ideal. And then consensus and collaboration is a big part of doing all of this. These are some references. So this is what we call the unified API document. This is our living document for what we all agree should be sort of the unified way an SDK for Sentry should look like. And we constantly update it whenever we make changes to it. The OpenTelemetry specification is also fun to read because they also solve very similar problems to us, but maybe in slightly different ways. So this is what the context I was talking about, that very heady sentence that was linked earlier. That's there. And slides I made with this very cool tool called Remark.js. So thank you.
Thanks a lot, Neel. We have some questions. The first question is, have you ever explored building a common core to all the libraries you're ever building, for example, in Rust or C, and then binding that using for and function interfaces?
Like generating, auto-generating stuff.
Yes.
Yeah, no, we never thought of that. But I think some other companies do that. Like AWS does that for sure. Like it just automatically generates a lot of bindings. But I don't think we ever looked into that. Also because we're trying to do stuff that might not generalize over everything. Something like that.
Right. And did you try in Rust macros or default implementation traits to inject your code without requiring an explicit wrapper?
I think our Rust SDK has a couple of macros, but I don't think we went very far into exposing everything as macros. But there's something there. But again, I'm not a Rust expert, so I'll look into it.
And
Okay.
Sure. And do you need to reach 100% consensus to go on? For example, I think in this unified API?
No, not 100%. So usually we have drivers for each sort of thing. So there will be 1 or 2 main drivers who will make a proposal and stuff, and then people can leave feedback. But ultimately, it's on the drivers to sort of just decide and move on, because you need that. Otherwise, you can just reach a deadlock and nothing gets done. Something like that. No.
Great. Are there any more questions? You can also raise your hand if you have additional questions. Don't need to put them into Slido. Yes.
Thank you for the talk. In the Python SDK, where is the monkey patched? well is the monkey patch performed? Like it's the import or it's the init function? And if you can elaborate a little bit on how it is
So the
performed.
so the Sentry init function does a bunch of stuff. It will first check whatever libraries you already have. So if it finds you have Django, it will then run a bunch of functions that go in and patch Django's request handlers, for instance, and so on. Yeah, request handlers, database queries, all sorts of stuff. Yeah, middleware views and stuff like that. Yeah, and then we record all of these things, and yeah, you see them in Sentry. Yeah.
All right. Any more questions? And thanks again to Neel.
Thank you.